I press the recording again, and for me it will be interesting to have the comparison, this formalism and Milton-Chung. So
okay, yeah.
So,
So now we want to do basically classical simulation, right? And yeah, if you look at Gutzmann-Neal theorem, usually what you simulate stabilizers, so and the evolution of stabilizers under Clifford action, and then you do some stabilizer measurement. And the idea is that this protocol is you can simulate this protocol in polynomial time on a classical machine. Yeah, the point is, first we need a stabilizer, right? Stabilizer state, so to say. So we start from a stabilizer state, but this stabilizer state is basically described by a subspace M of the phase space, which is isotropic. And actually, yeah, if P is equals to, you just take M alpha. But this description is easy because M is described by a basis. So you just take basis elements for this subspace, and yeah, so you need basically n elements to describe your stabilizer states. Sorry, n vectors in the phase space to describe your stabilizer state. So yeah, this point is, I think, is easy to see why it's easy to simulate. Basically, the first point would be transformations under Clifford. Now, between the odd and even characteristic, we have two different behaviors. First, suppose that P is not 2, and we saw that basically a Clifford was an operator mu of GV that is just mu of G W of V, right? And yeah, this is just a phase factor. And actually, yeah, because the idea is you know how this thing is acting on value operators. So yeah, because you have that mu of GV W of U, and now mu of GV dagger. This is by construction. I write things more explicitly. So this is mu of G W of V, W of U, W of V dagger, mu of G dagger. And then this action here, this is just -1. Sorry, it's just the character. And then you have VU. This is, I didn't recall this time, but this is one of the properties of while operators. And now we have mu of G W of U, mu of G dagger. And then you are done, because now this is just the character. And then this is W of G U by definition of the action of mu on while operators. So what we have to do to simulate or to evaluate the action of a Clifford on two while operators is this product here and evaluate this thing, right? And this is something that you can do classically. Yeah, this is just matrix vector multiplication or just evaluation of a symplectic form. And yeah, and so when you update a stabilizer state, which is described by vectors v1, vn, you would just update these vectors with your symplectic matrix. So yeah, you have this basis here, and this you just get another basis that is g1, gbn, and this is basically how you will update your state. And now the difference is we have a difference for p equals 2 because these expression here are different, right? Actually, is that here you need to take care of other phases because when you evaluate this thing, sorry, it's something that you still can do, but yeah, what's happening here is that it's kind of similar. You have first this factor here that is equivalent to this chi, and then you also have w of g times u, but there is another phase factor that is function alpha g of e. This function can be evaluated. Evaluated in time O or n cube. So yeah, in the qubit case, this update is slightly less efficient, one order less efficient. But yeah, this is still can be done. And what is this function? This is related to the compatibility condition of the beta functions. That's the way you would evaluate this thing. But yeah, you have this prescription in this case, but then everything is the same. And the last thing that you do is yeah, stabilizer measurement. So yeah, namely you want to measure a while operator WB or WA. Let's start to the notation in Marcus thesis. And now you basically have some cases because yeah. How to write things. First, you have you have an isotropic subspace associated to this state, to this operator. Yeah.
When you measure W, it's like the ±1 spectrum, so the projectors will be 1 plus W. Yeah, that's the idea. Or?
Yeah, but this is for qubits, right?
And for qubits, it's more complicated than yeah.
For qubits, for example, if you consider Z operators, you have all the roots of the unity. So
yeah. Okay. Yeah.
Yeah. That is also true for qubits, but for qubits is +1, plus or minus 1. Yeah, basically you have associated to this operator an isotropic subspace that is just generated by A. And now the idea is that you, yeah, okay, that's not really useful. You just check that AVI is equals to 0 for each I. Well, or for I equals from 1 to n. Now, if true, that means that yeah, basically your outcome, your state after the measurement is basically the same in the sense. Yeah, it's like sorry. If true, let's think first at the outcome distribution. So in this case, the out. Okay. Is just deterministic. And then you have basically the psi. Okay, I didn't add. Let's say a projector associated to this M psi. This is just 0 or 1. Okay, and otherwise, the outcome is just is the uniform distribution, so it's 1 over p. Think, for example, a Z operator measured over plus state, and then your outcome is 1/2. Otherwise, if you measure the Z operator over 0 state, your outcome is 0. And yeah, so these are for the outcomes. For the yeah, if you want to look at the post-measurement state, yeah, the idea is that in the first case, your state would be still described by the same generators of the stabilizer group, and so you don't have to update them, but you have to update them in the second case because A is not commuting with at least one of the VIs, and but the idea is that for yeah, if you in the second case, let's say, suppose for example that A V1 is not 0, but you can suppose that AVI is equals to 0 for I from 2 to n. This is because if for one of them is not true, you can just multiply for a suitable multiple of V1. So for example, because yeah, let me write this. If you have A Vj different from 0, now you can update Vj to lambda V1 Vj such that A Vj is equals to 0. When you do this update here, you're still in the same stabilizer. You're still describing the same stabilizer state, and then yeah, it's just a trick, this one, to make the description a little bit easier. But
Wait.
when you have this,
Sorry, you're multiplying the vectors now, or what is this lambda v1 vj?
yeah, sorry, yeah, right, plus.
You
If my pen is writing, would write,
you want to
but
write
yeah, it's a plus.
it's
Yeah.
a plus. Okay, yeah, and then you just
Okay.
yeah,
Yeah, you're right, of course.
it's a plus. Okay.
And then in this case, then you have other another, the state would be described by Lagrangian given by a v2 vn. So that's the what's happening in this case. Yeah. The thing is that in this first case, when you are in this case here, yeah, you don't have to do this update because A is commuting with all the basis vectors. And in principle, if you want to know the outcome, you have to evaluate the character, but this is done in linear time. Similarly here, the update is slightly more costly, but still it's done in polynomial time anyway. And yeah, it's compared to the standard Gutzmann-Nil theorem, is if you look at that, it's exactly the same, but we are describing things with vectors in the phase space and symplectic matrices. Just commenting this point. Because yeah, here you just describe this with the associated Pauli operators that are just the image under the representation W of this point. And yeah, here is kind of the same. You, especially for this update here, you just conjugate each Pauli operator with the corresponding Clifford. And yeah, and the stabilizer measurement step is exactly the same. The advantage of using this formalism is, for example, on the in this second step, because usually when you do Gutzmann-Nil theorem, you work only with the generators of the Clifford. Because you know, for example, the Hadamard how transform the Z operators and so on. But here you can just do that for any arbitrary Clifford because you can do this for arbitrary symplectic matrices.
So you don't need to compile somehow.
Yeah, it's something that you in principle don't need to do. This at a theoretical level.
Okay, okay.
And of course, yeah, this is true also for qubits because actually it's even easier because you don't have to evaluate the alpha function at this point.
Yeah, yeah. I missed a little bit the measurements.
Yeah.
Okay, so we are measuring the A, and if it's deterministic, there's no update, and the
Yeah.
then you have the outcome distribution is 1/PS.
Is 1/P when it's not commuting with all of them.
When yeah. So
when it's failing for at least one vector.
So it will be a flat distribution, and then
Yeah.
you said okay. And then I need to update my stabilizer state, right? After the measurement.
Yeah, in this case, yeah.
And can you say again how I will be updating it? So I'm doing this measurement of A's.
Yeah, it's just these last lines. So suppose that you don't commute only with V1. Sorry. Okay, sorry. No. It's just you replace your vectors with the new one, the newer one. So here we were assuming that A is not commuting with V1.
Yeah.
And so, but A is commuting with V2 Vn,
Yeah.
and you just replace V1 with A. So yeah, your state after the measurement will be described by this Lagrangian.
So I will have to also sample with 1/p probability, or so. So no matter what the random outcome is, I always replace it with the same thing.
Yeah. The outcome is more if you want to, well, in this case, but when you describe your state, you just need the set of you need the basis for the Lagrangian subspace, right? So you just need to find a new basis, and
So
that
now
will be,
I was applying a projector, and so I fix it to be a, yeah, and that's my update.
yeah.
And I need those commuting relations so that it was Lagrangian before, and then it stays Lagrangian before, and so I keep the state. Yeah.
Yeah, and you need n vectors to describe a stabilizer state. So
And if it happens that the other ones don't commute, I have this V1 there as well.
if you other ones do not commute, you do this this transformation here. I mean, you just update in a fancy way your other non-commuting vector, so
is it
that it will
like a
commute.
symplectic Gram-Schmidt or something like this? Or?
Uh,
Because you're somehow removing some, a little bit like a projection.
yeah.
But the idea will be that I will do it until only one is left, and then I will apply that to this one, and just keep all those V1 shifted vectors, and that will be my new Lagrangian generators. Yeah.
Yeah. If you need to update, yes, for example, you will have a new VJ's vector that is combination of the old VJ and V1, and you still replace the V1 with A.
And so in some way all of them will be affected, and it yeah. So even though I replace only one, the other ones are also somehow affected, and so this replacement of only one of them will actually affect the whole basis in some fairly non-trivial way. Or?
I think if you are really unlucky,
I was thinking in the generic case, probably like all of them are non-commuting.
yeah, of course, it may happen, I think. But yeah, it's something that still you can do easily.
Yeah. All right. Okay. So would you still like to summarize a bit, or we just finish for today? I think this is.
Yeah, I think we can just finish. We are
Okay,
already.
Yeah, thanks for this. That was very insightful. I learned new things. Okay, super. So we meet next week. Thank you, Mirko.